Welcome to new lecture on modulation. We will start this lecture by revising some of the concepts. So, what we said that modulation basically deals with conversion of a binary sequence into waveforms. Okay. So, binary sequence means sequence of ones and zeros. So, for example, we have a binary sequence, and then what the first step we do in modulation is we convert this binary sequence into complex numbers. For example, here we have complex numbers A0, A1, A2, A3, A4 and A5. We can also map it into real numbers, but for general I am assuming it to be complex numbers. Intuitively you can understand it as you are having train of impulses, and the weights of these impulses is decided by these complex numbers. So, for example, this impulse has a weight A0 and A0 corresponds to this complex number. So, we have got the binary sequence and we have converted this into impulse train, and the weights of these impulses are the complex numbers. Mathematically we can understand it by this expression. This just tells me that I have impulses which are t spaced. So, t is the spacing between these impulses, and the weights of this impulse is a case. So, a case means A0, A1, A2, A3 and so on and so forth, and I have this t shifted impulses k times where k goes from minus infinity to plus infinity. So, that means I am going to have unending impulse train. Okay. So, this is basic idea how you represent this weighted impulse train by this expression mathematically. So, after we have got the impulse train, the next step that we do is we pass this through a filter. Okay. So, we have assumed that I have a filter which has got the impulse response Pt. So, on passing this through a filter, mathematically what would happen is that this impulse train would get convoluted with the impulse response of the filter, which is Pt, and this impulse response of the filter I have assumed to have such a shape. That means this is a kind of a pulse which goes from minus t by 2 to plus t by 2. Okay. So, this is the impulse response of the filter, and the effect of passing this impulse train through the filter is that you need to convolve this with such a pulse. Convolution of this pulse with this impulse train can be simply achieved by just putting the caps of this pulses on these impulses. So, you pick this pulse, you put a cap of this pulse around this impulse, you get this waveform. Then you put this cap around this impulse, you get this waveform. You put a cap around this impulse, you get this, and so on and so forth. So, basically what you would end up with is an analog waveform. Okay, where this waveform is this cap, and the height of this cap is decided by the weights of these impulses. So, after you have passed this sequence through a filter, you will get an analog waveform, and this analog waveform will be a baseband waveform, meaning that most of its energy would be centered at DC. Then next, after we have achieved analog waveform, what we would do is we would multiply it with the cos omega naught t. Cos omega naught t on multiplication would induce rapid phase fluctuation. So, you would have a waveform like this, where the envelope of this waveform is decided by this analog waveform, and then this oscillates very fast at a frequency of omega naught. So, what we are discussing is the typical steps that happen in a modulator. These are typical steps. Not all modulators would do exactly like this, there might be some variations, but it is a good idea to start by thinking about a modulator along these lines. So, let us look at the block diagram of the modulator, which we have seen couple of times. So, we have a binary sequence. Remember that a binary sequence is a sequence of ones and zeros, and this binary sequence is then converted into samples. Okay. And samples, we know it is nothing but it is a weighted train of impulse. This weighted train of impulse then passes through a filter with impulse response Pt, and we get a weighted pulse train instead of an impulse train. And then this is a baseband signal, and this baseband signal is converted to passband signal by using a multiplier. So, what we are interested in this lecture is in understanding the impact of this mapping of binary sequence to these AKs, and what is the impact of impulse response of the filter on the spectral occupancy of various modulation schemes. Okay. So, remember what we have also said in one of the previous lectures, that if we focus only till this part, we can also say modulator as line coder. Okay. So, in fact, in this lecture we will be dealing with the spectral description of various line coding schemes. So, line coding means you convert a binary sequence to samples and then you convert these weighted train of impulse into weighted pulse train. Okay. So, this is line coder. So, line coder is same as modulator if we are ignoring this block. Let us see something more. So, we have said in the last lecture that we want to understand this waveform. So, ST is the waveform that is available here at this point, and we can think about this as this. So, here this Bn is the same thing as AKs. Sometimes I am using AKs, and in this context I am using Bn. So, Bn are same things as AKs. Okay. So, in general I can allow them to be complex numbers. All right. Now, see this, that this Bn are multiplied by the common pulse shapes. Okay. So, each Bn is multiplied by the same pulse shape, and this kind of modulation is known as linear modulation. So, linear modulation is the kind of modulation where you have the same pulse shape. Okay. Now, what is the impact of having this Bn as complex numbers? Let us see it. I have a slide for this. So, if I assume Bn as a complex number, it can be thought as a sum of real part and an imaginary part. So, St can be written down like this. So, I am just decomposing Bn into its real part and its imaginary part. Then you can multiply this with Pt minus Nt, and we get one real waveform which I call SCT, and you have another real waveform which I call as SST, and ST can be thought as just the sum of SCT plus J times SST. So, this is the impact of assuming Bn to be complex. Then ST is built up of two real waveforms, SCT and SST. Okay. ST then will be complex. After having understood, let us come back to this. So, we want to take the Fourier transform of ST to calculate the bandwidth, because typically that is used. But one problem that you would run straight away when you want to calculate the Fourier transform of this is, because we always assume this Bn to be stationary. Why do we assume to be stationary? We have talked about this when we have discussed random processes, and we have said that the stationary waveforms are the practical model that we want to use, because we do not want to say when this waveform stops and for what period it runs in. Okay. So, to avoid those kind of difficulties, we simply assume that the waveform is stationary. Now, if this Bn sequence is stationary, and if this runs from minus infinity to plus infinity, it needs to run from minus infinity to plus infinity. If Bn is stationary, then we know that the energy of the sequence is infinite with probability 1, and then you would have problems in finding the Fourier transform of this waveform, because the Fourier transform of infinite energy waveforms do not exist normally, right. So, you are not sure whether the Fourier transform would exist or not. Sometimes it exists if we allow impulses, but in general you cannot say whether the Fourier transform of this waveform would exist, because it has got infinite energy. To avoid those kind of mathematical problems, what we do is we define another signal as T naught t, where as T naught t truncates St. So, instead of St going from minus infinity to plus infinity, what we say that St goes only from minus T naught by 2 to T naught by 2. Okay. So, we are kind of making it a effectively stationary process if T naught is pretty large. Okay. The effect of truncation in this could be understood by limit n. So, instead of n going from minus infinity to plus infinity, what we can assume that n goes from 0 to n minus 1, where n is pretty large, but it is not infinity. Okay. It is just dealing with mathematicians, nothing else. We are just trying to make this waveform only exist for a finite duration. So, the total duration we said is T naught, and if I have n samples and the difference between the two samples is T. So, the total duration would be n times T. It is a good idea to note this down, that T naught is n T. So, now we can take the Fourier transform of this. That happened for our good, because now this S T naught T is having finite energy, and if it has a finite energy, then you can take the Fourier transform of this. Now, the Fourier transform of this is defined. So, this is S T naught F. Okay. So, we did cover everything in the last lecture. I am just revising, giving it a better look probably. So, what we said in the last lecture, that energy spectral density is nothing but it is the mod square of the spectrum of a signal, that is the energy spectral density, and power spectral density can be defined by taking the limit of this expression for T naught tends to infinity and divide it by T naught. So, energy spectral density divided by the total duration of the signal and make the total duration of the signal tending to infinity, but not infinity. Okay. So, this is how we would define the power spectral density. So, we covered all of this in the last lecture, and now the time to learn new stuff, and the one thing that we will do is to find out what is this value for different kind of waveforms. So, let us start with this. This is the same formula, that S T naught T B n, and this is P t minus n t. And one thing that we need to do now is to take the Fourier transform of this. We can take the Fourier transform of this because n is finite, n is very large, but it is finite. So, taking the Fourier transform of it, B n we know it is a constant with respect to time, B n is not a function of time, P t minus n t is a function of time. So, it is a constant with respect to time. So, I have B n. Now, I have to take the Fourier transform of this pulse. Fourier transform of this pulse I have assumed is P f into e to the power minus j 2 pi f n t. This is by the properties of Fourier transform. So, if we assume that the Fourier transform of P t is P f, then the Fourier transform of P t minus n t would be P f times e to the power minus j omega n t. So, omega is 2 pi f. So, using these properties of Fourier transform, we can quickly calculate the Fourier transform of this expression. It is simple. Now, so we have calculated the Fourier transform. Now, the task is to calculate energy spectral density, which is mod of the spectrum of S T naught T square. Okay. And we have seen it several times that the best way to compute this quantity is to multiply this quantity with its conjugate. So, here we have to multiply S T naught F with its conjugate. Okay. So, that will give me mod square of S T naught F. So, it is also easy, and that is why we are not writing everything today. So, we have S T naught F, which is this we derived in the last slide, and then we have to multiply again with this, but we have to take the conjugation. So, if we have to take a conjugate here, so it becomes B conjugate m, conjugation here, we got a conjugation here. When I am taking a conjugate of this quantity, this minus will become plus. Okay. And everything else remains same. I have also introduced one more change, that instead of n going from 0 to n minus 1, now we have m going from 0 to n minus 1, and why we do this, we do it often, and this is because we want to preserve the cross components. So, for example, in this multiplication you would have B 2 multiplied by B 5, right. So, all these things become easy if you assume a different running variable. This is commonly the case. Okay. This we do every time we need to multiply two summations. Okay. So, we have kind of trying to calculate the mod S T naught F square. Now, one thing that you can see here before we move to the next slide, that this P f is not a function of n. So, this is a constant with respect to summation. So, we can pull this out. Similarly, this P f conjugate is not a function of m. So, this could also be pulled out. So, pulling this P f and P f conjugate out of these two summations, what you end up with is mod P f square, okay, mod P f square, because this is nothing but P f into P f conjugate. Okay. So, that is this part is taken care of. Now, again from Fubini's theorem, we do not worry about the order of summation, we simply club them together. So, now I have taken all two summations together. What you end up with is Bn into Bm conjugate into e to the power j omega, and here I was having omega m and here I was having omega n with minus. So, when I add these two things, I get omega m minus n. So, this is here j omega m minus n t. Now, what we do is we try to substitute n minus m as k. So, first thing that we try to understand, what is the limit of k, from where to where k goes, and if you want to see that, what should be the maximum value of k? Maximum value of k would happen when m is 0, because m is anyway positive, right. So, if I assume m as 0, I should get the maximum value of k, which is the maximum value of n, which is n minus 1. So, this is the maximum value of k. Similarly, to find the minimum value of k, I need to assume n as 0, and then I find out the minimum value of k, which is the maximum value of m minus. So, minus maximum value of m minus n minus 1, because maximum value of m is n minus 1, right. We are running this summation from 0 to n minus 1. So, in short, k should go from n minus 1 to minus n minus 1. Now, one thing that we should do now is to replace this n minus m with k. So, this should become e to the power j omega minus k t. Okay. So, this is what I have here, nothing difficult. So, mod P f square, because it was already here, the summations are intact, I have not still changed the limit or anything, Bn into Bm conjugate into e to the power minus j omega k t, and we know that m is n minus k. Now, we want to now change the limit. So, what we do, if we see this is not a function of n. So, first what we want to do is to have two summations, a summation with k and a summation with n as a running variable. So, instead of m, because m we have substituted as n minus k. So, now I have two variables n and k. We want to get rid of m. We have got rid of m by using this change of variables. So, now we have two variables k and n. Okay. As you can see, m is replaced by n minus k. So, in this integration there was m here, we have replaced it with n minus k, and so I have one summation with respect to k goes from minus n minus 1 to plus n minus 1, and I have another summation with respect to n, which as before goes from 0 to n minus 1. Now, if you see here, this was only a function of k. So, I have pulled this here, and this I have combined all terms which has n as a running variable. So, I can reduce this summation into this summation. It is trivial kind of, there is nothing difficult in here. Now, autocorrelation function we define using this. So, this quantity should tell you that it is an autocorrelation function. We have divided by n, and where limit n tends to infinity. Now, you should also see that when we are having these quantities like autocorrelation function or other things, let me write. So, if you are having RK autocorrelation function, there are two ways in which you can calculate this, either by doing a time average operation or by calculating the ensemble average. So, we have seen all this before, and for an ergodic process, this time average is same as ensemble average, and we have also said all practical processes are ergodic processes, and so we can either calculate this autocorrelation function using a time average operation, or we can find this using ensemble average ideas. Whichever idea is good, we can use that. So, currently I am finding autocorrelation function using time average idea, and after a while we will do the same computations using this ensemble averaging or statistical averaging idea. So, right now we are trying to use this time average idea, which is more convenient at this point. So, autocorrelation function or time averaged autocorrelation function, if you like to call it in that way, is given by this quantity, where you have to take the limit n tends to infinity. Now, if you want to replace this thing, you should realize that this is nothing but r k times n, because this whole thing is r k. N is anyway very large, we are assuming n to be very large. So, this quantity is nothing but r k times n. So, substituting that in this expression, what do we get is mod p f square, everything remains same. So, let me put it here. So, this is same, this is same, this quantity we have replaced with r k times n. Okay. So, now you look at this, what do you see? So, this I plug here. So, this is r k e to the power minus j omega k t summation k going from minus of n minus 1 and n minus 1, where n tends to infinity. This is nothing but it is the Fourier transform of autocorrelation function, and Fourier transform of autocorrelation function is nothing but it is the power spectral density. Okay. So, what you have is a power spectral density of input sequence. So, which we denote with Z I of f. So, power spectral density I represents input sequence. So, finally, after all this maths, what we get is mod p f square. This quantity we said is Z I f, and anyway we have n here. So, we got this. Finally, coming back to what we were deriving and see what we have got now. So, by definition we said power spectral density is this quantity where limit T naught tends to infinity, and this quantity we have already evaluated now. We have evaluated the energy spectral density, which we have derived. It is nothing but mod of p f square Z I f times n, using this value of energy spectral density here, and T naught, as we have said, is nothing but n times t, number of samples into the time difference between the samples. And now, instead of putting T naught as infinity, we can put n as infinity, right, it is one and the same thing. So, now cancelling n by n, what we get is a very neat formula. It is power spectral density is mod p f square by t into Z I f, where Z I f is the power spectral density of the input sequence. So, this is one thing that you should know and remember, it is a very useful formula. So, one big thing from here to see is that the power spectral density depends upon the square of the magnitude of the spectrum of the modulating pulse. That means, which pulse you choose decides in some sense the power spectral density. So, we have to be careful with the choice of our pulse. Second thing, it also depends upon the power spectral density of the input sequence, and we will see some examples of how it influences the output power spectral density. So, just to avoid any confusion, let me also say that this is a power spectral density corresponding to ST, okay, and this is power spectral density corresponding to Bn. Okay. So, this you have to see carefully. So, this is Bn, this is power spectral density corresponding to Bn, and this is the power spectral density corresponding to St, okay, and these are related by this. And this formula is also valid only for linear modulation. So, we are using just linear modulation, and this you have to be careful with. Okay. So, finally, PST of the analog waveform. So, when I am saying analog waveform, I mean ST. Just keep this in mind, otherwise it can be confusing sometimes, because we have several power spectral densities going in here. So, we are saying the power spectral density of ST is this quantity mod square of PF, where PF is the Fourier transform of the modulating pulse, divided by T. T denotes the spaces at which bits arrive or you want to create sequences, and ZIF is the power spectral density of input sequence. Now, there are various ways to write it, more powerful than this. All these equations are derived simply from here. We know that anyway ZIF is, what is it? It is the Fourier transform of we have already seen this. ZIF is the Fourier transform of the autocorrelation function of the binary sequence, right, nothing great in that. So, instead of writing ZIF, I have written it in a somewhat a strange way in this, because this is quite useful. So, what I have done is I have pulled out R0. So, I have R0 here. So, this you can interpret as R0. So, I have pulled out R0, then what I end up with is the summation except R0 point. So, this is the summation, this here k goes from minus infinity to plus infinity except k equals to 0, because that I have included here for some reasons which will become clear. The reason is simple, that this is probably more useful than combining everything together. Okay. We will see some examples, and then probably you will appreciate the use of this expression. Anyway, it is one and the same thing, just it is more convenient to use it sometimes. So, k goes from minus infinity to plus infinity. Instead of that, I have assumed k going from minus infinity to plus infinity except k equals to 0, and k equals to 0 point I have pulled out. And this expression can also be converted into this expression. Again, sometimes we will use this, sometimes we will use this, both are pretty useful. So, it is a good idea to see that there are various ways in which you can find the expression of the power spectral density. How we get this from this? Let me explain that as well. It is tedious, but it is also trivial. So, let us just see, we are trying to derive this expression from this expression. So, we have R0 plus Rk e to the power minus j k omega t. So, this is R0, let me put it, okay, so that there is no difference between the two notations. And now you see that k goes from minus infinity to plus infinity except k equals to 0. So, I can break this down into two summations where k goes from 1 to infinity, everything same, and k goes from minus infinity to minus 1. Anyway, k was not including 0. So, I have broken down this summation into two summations, okay, that is good. Then I do not do anything, but here what I do is I introduce a change in variable. So, I have used m instead of k, I am using m, and I am saying m, let m be minus k. Okay. So, that means k should be replaced by minus m. So, I am replacing this k with minus m, this k with minus m. So, this becomes positive, and the limits should change. Instead of k going from minus infinity to minus 1, m should go now from 1 to infinity. Okay. Just normal exercise. So, now I have this, and now realizing that r of minus m is same as r of m, because autocorrelation is an event function, I can rewrite this expression just by replacing r of minus m with r of m. So, everything remains same, just I have replaced r of minus m by r of m, because they are same, it is an event function, autocorrelation is event function. So, r of minus m is same as r of m. Okay. So, we have got this. Now, let us see what we do is, now I do again something trivial, because this is with m going from 1 to infinity, m is just a running variable. So, I can very well replace it with k, nothing would happen. So, I am replacing now m with k, and I am getting the same expression. Let me try to put everything together. So, I had this, so this is same as this, just here I replaced m with k, okay, nothing changes, just instead of m I have got now the k. Okay. Now you see everything has a same almost, other than these complex exponentials which are rotating in different directions. So, I can pull this out, I can take this summation r k common, this I can multiply with e to the power minus j k omega t from here, and I have e to the power j k omega t from there, and this you know is cos k omega t times 2, and this is what we have. So, it was a very simple proof, nothing difficult, but it is a very convenient thing to realize, to remember, because it would be useful, right. So, let me remind the three expressions of power spectral density that we will use. This is simple to state, and a convenient expression is this, and a convenient expression is this. Okay. So, there are three ways to state the power spectral density. Let us now see some examples, and the example of line coding mechanisms that I am starting with. The first one is the polar signaling mechanism or polar line coding. So, in polar mechanism what happens is you can map a to 1 and you can map minus a to 0. So, we have a binary sequence 1 or 0, 1 is mapped to a and 0 is mapped to minus a. There is nothing sacrosanct in this mapping. What you can also do is you can map 1 is mapped to minus a and 0 is mapped to a, and in fact this mapping is usually preferred. Okay. And what is the reason for this? The reason is that if you use this mapping, the XOR of these binary sequence is same as multiplication of these numbers. Okay. So, if you do the XOR operation on the binary sequence, for example, if I have these two binary sequence and if I choose positive for representation of 0 and negative for the representation of 1, and if I see the XOR operation of these two binary sequence, I obtain this sequence, and in this case I am mapping positive voltage to 0, negative voltage to 1, positive to 0, negative to 1. Similarly, I can have the representation for this binary sequence like this, and if I multiply these numbers I get some negative and positive numbers. If I assume negative numbers to be 1 and positive numbers to be 0, I see that the multiplication of these numbers is same as the XOR operation of the binary sequence, and this equivalence is sometimes convenient in certain applications. And though for our case it would not make a difference whether you use this mapping or this mapping, but for practical systems this mapping is usually more preferred, and the idea is that we want to have the equivalence between XOR operation for binary sequence and multiplication operation for real numbers. Okay. And that is why this is usually preferred. But for this course we will continue using this mapping, and this is because it would be more consistent when we study line coding schemes. So, even though this is usually preferred, but for academic reasons I would continue using this mapping. Let us see how we can find the power spectral density for polar signaling scheme, and as I have said I will use this mapping where 1 is mapped to a and 0 is mapped to minus a, and first thing that I need to find is r of 0. What is r of 0? By definition you have to compute this summation if you are interested in finding r of 0. So, here the sequence is the same as this sequence, but it comes with the conjugation, but because I am assuming that these numbers a are real. So, if you take conjugation or if you do not take conjugation, it would not matter. Okay. So, let us assume that I have a binary sequence, some binary sequence does not matter, and the next binary sequence that I have to take should be the same binary sequence as I have assumed here, because this is same as this other than the conjugation, but conjugation really does not matter. So, I will have the same binary sequence, and then I can map this binary sequence to some voltages. Like this. So, here I am mapping these binary sequence to these voltages. And you can see what happens is that if you have 1, here also you will have 1, because this sequence is same as this sequence. So, if you have 1 in this sequence also you will have 1. If you have 0 in this sequence also you have 0. So, because these sequences are one and the same thing. So, I can have two situations, either I will have 1 or I will have 0. If I have 1 in this sequence, in the next sequence also I am going to have 1. Okay. So, if I want to find out what is the result of this multiplication, here I am multiplying the numbers associated with these binary digits. Okay. So, if I am associating a to 1, this one will also be mapped to a. So, I will have a square. For these zeros I will have minus a multiplied with minus a, which again will be a square. So, whether you have 1 or 0, every time we will be getting just a square. Okay. So, this summation you can think yourself will be nothing but it will turn out to be as a square, right, because the product of this multiplication will always be a square, whether you have 1 or you have 0. Okay. So, the average will also be always a square. Let us now see what happens if I have R of 1. If I have R of 1, then this sequence would be delayed by 1 bit corresponding to this sequence. So, if I assume a binary sequence, this Bn minus 1 will be a delayed version of this. But this Bn and Bn minus 1 are not the binary sequence, they are the voltage corresponding to this binary sequence. So, if I use the mapping which I have used before, so one is mapped to A, this one is mapped to A, this is minus A, A. So, I will have and so on and so forth. Now, if you have 1 here, you can have either 1, so this situation, or you can have 0. These bits are statistically independent of each other. So, if you have 1 here, you can have very well a 0 or a 1, it is delayed by 1 unit. So, you can assume that if you have 1 here, you can very well could have had 0 or 1. So, if I have 1 in this sequence, I can have 1 or 0. Similarly, if I have 0, you can have 0 or 1, and all these events will be equiprobable if you assume that the probability of 1 is same as the probability of 0. Okay. Corresponding to these binary digits, the voltage mapping would be A and A, and we are interested in finding their product. So, this will be A square, this will be A times minus A, this will be minus A square, this will be minus A times minus A, this will be A square, this will be minus A times A, this will be minus A square. Okay. And each of these pattern would happen n by 4 times if I am assuming n as the total length of the sequence. If n is very large and all these 1s and 0s are equiprobable, I can assume that each of this pattern would happen for n by 4 times. So, I have 1 by n, each of this product would happen for n by 4 times, and you have a contribution of A square minus A square plus A square minus A square, and you can easily see that this will be 0. Okay. So, R of 1 is nothing but it is simply 0. Similarly, you can find it yourself that R of n will also be 0 for n greater than 1, Okay. In short, I have already found that r of 0 is a square and r of n is 0 for n greater than or equals to 1. This we have already proven, this I leave to you to prove, and in short I can arrive at these two conditions. Power spectral density, as I have already said, can be given by mod square of P f divided by T r 0 and these terms, and because all of them is 0, if k is not 0, then I simply end up with the power spectral density, which is mod square P f by T times r of 0, and r of 0 is nothing but it is the power of the data sequence, binary sequence. Okay. This we have already seen in one of the previous lectures, that r 0 corresponds to the power of the sequence. P d you can see is nothing but this quantity, all right, and this is r of 0. Okay. So, we have derived a very useful relationship of power spectral density for a polar signaling scheme. Now, let me assume a pulse shape P t, and the pulse shape that we are choosing is rect of t divided by t by 2. Okay. So, if you see this, what we are doing is we are saying that if I assume that this bit duration is t, my pulse duration is only t by 2. So, the pulse duration is t by 2. That means this pulse would take a value 1 or a for a certain duration, and then it will drop down to 0, and such a pulse is known as return to 0 pulse. That means it returns to 0 within a bit duration. You can also have a non return to 0 pulse, that means if it is 1, it remains 1 for the entire bit duration, it does not drop down to 0 within the same bit duration. Okay. So, this is how we can have different kinds of pulses. So, here we have assumed a return to 0 pulse. The Fourier transform of this pulse P f, you know from signals and system course, it is very easy, t by 2 comes here and then you have sinc f t by 2. This is the Fourier transform of this pulse. Now, the power spectral density that we would have is mod P f square. P f was this. So, mod P f square would be this into a square corresponds to P d, and we have t. We can simplify this to get, so t cancels with t. So, we have t by 4 a square sinc square f t by 2. Certain important things that you need to see is where the first null happens, right, because that decides the bandwidth of my waveform. Okay. So, if I am trying to get the position of the first null will happen when this quantity or the argument of the sinc will become 1, and this will be the case when f becomes 2 by t. So, the bandwidth is 2 by t and 1 by t is bit rate, which we say R b. So, R b is the bit rate. So, bandwidth is 2 times R b, 2 times the bit rate, and we will see short while from now or maybe in a next lecture that the minimum bandwidth required is R b by 2. So, this is the minimum required bandwidth, and this signaling scheme is taking a bandwidth which is 4 times the minimum required bandwidth. So, it is wasting a lot of bandwidth, and this is the drawback of this signaling scheme. Let me plot the power spectral density of this signaling scheme. The power spectral density, as we have already derived, is given by this expression, which is this, and it is a sinc square. So, typically the shape is of that kind, it decreases with frequencies and so on and so forth, and this amplitude, the highest amplitude here, it will be a square t by 4. The first null happens at 2 by t, 2 by t corresponds to 2 times the bit rate. Okay. Let us see the disadvantages of this signaling scheme. The bandwidth is 2 times Rb, so that is wastage. It has non-zero DC power. So, if you look at DC, 0 frequency is having substantially high power. Okay. That is a disadvantage. That is a disadvantage because of several reasons. One important reason is when we were using twisted pairs for echo cancellation etc., you were using a transformer. I have a picture for that. So, this is a typical example of a echo cancellation circuit. So, echo cancellation circuit used to use a transformer. So, transformer does not pass DC, right. So, if a signaling mechanism has lot of DC power, this will go waste. Otherwise, you cannot use such a signaling mechanism wherever the transformers are used, right. And not just transformers, we also use AC coupling circuits for impedance matching and so on and so forth, and you will also lose power if you use such a signaling scheme. Okay. So, this is a disadvantage. Typically, you do not want to have a large DC power. Okay. It does not do any error detection. That means, for example, if I have a binary sequence like this, if I have a waveform like this, and because of error if this part flips over, then there is no way to tell that an error has happened. There are signaling schemes where you will be able to detect some errors, if not all. Okay. We will see some examples of that, but polar signaling scheme as such does not do any error detection. Good point of this is that it is transparent to ones and zeros. Transparent to ones and zeros means that, suppose I come back to this diagram, if you have a long trains of zeros, if you have zeros continuously, right, even then you would have transitions. Okay. So, if you have a 0, then if you have a 0, there would be a transition. If you have transition, then it is easy to keep your receiver synchronized with the transmitters. Okay. So, this for synchronization, it is important that your signaling mechanism is transparent to ones and zeros transmission. So, this is its advantage. The another advantage is easy clock recovery, and this could also be seen very easily if you have a polar signaling scheme. If you rectify this, this will flip over, changes to this side. So, we have a clock, and so very easy clock recovery mechanism that you can use if we use a polar signaling scheme. So, these are the advantages of polar signaling mechanism. So, with this we end today's lecture. Today we have understood the important ways in which we can calculate the power spectral density. Power spectral density, we said, depends upon the two things. The one thing is that it depends upon the square of the magnitude of the spectrum of the modulating pulse. That means, it depends upon the mod PF square, and it also depends upon the input power spectral density. Okay. So, and then we have discussed an important example of a polar signaling scheme, and we said that a polar signaling scheme has certain advantages and disadvantages, and at this point it seems that it has some critical disadvantages, particularly with respect to the bandwidth. It takes the bandwidth twice of the data rate. So, that is too much because the minimum required bandwidth is Rb by 2. Then also it has non-zero DC power, right, and which would not be a good thing if you assume that you have a transmission over twisted pair lines which uses transformer, or you are using it over a digital communication system which is using AC coupling for impedance matching. In the next lecture, we will see important examples of other signaling mechanisms like unipolar signaling mechanisms or a bipolar signaling mechanism. Thank you.